in theme 1, we had this general approach where the way that you knew the model and the parameters and the numeric values of the parameters was by looking those things up in sources or measuring them with a ruler or whatever, right? So if we think about our cup model, right, the way that we knew, for instance, the relationship between the volume and these various heights and diameters and so on, these things were all geometrically fixed. So we didn't guess them. We didn't kind of say, oh, I think it's approximately like h to the 2.3 power. That never happened. We looked in the book, or we looked online, or we kind of did some kind of an integral or whatever. We did the math. The math told us the formula, right? And so these are known as first principle, or in many cases, people will have this kind of spectrum that they draw, and they'll draw from what they call white box models, right? And white box models, the idea is that you have a box, which is a little bit like our block diagrams, right? And on the one side, you've got your inputs that go in, and you've got your outputs that go out. And the idea of a white box is that you can see all of these formulas right there inside the box. You can basically say a white box is actually a transparent box, right? In other words, you can see all the way into the model. You can see the choices that the designer of the model made. They're all inside the model right there. So when we talked about a dynamic model, and the kind of model that you wrote down for part 1 of the project was this kind of model. It was a first principles model, and it was based on, and it was like I would classify it as a white box model. Now, then we went on and we said, okay, well, sometimes we can simplify these equations by linearizing and doing all the stuff that we've been doing all the time in the subject. And we moved through a couple of themes where we simplified these, and we ended up with basic like first order prototype. So we can say, okay, if we have a linear time invariant model, we can write that like k over as plus 1, say. And that's now we can still see the model equations, but I want you to understand that part of that linearization process means that there will be many models. It's like a funnel, right? That there will be many models that have the same linearized representation, even though they were different to begin with. Does that make sense? Because we're making this approximation, and it's almost like you're fuzzing or like you're zooming out. And so a lot of times, like if you zoom out really far, you can see there's a person there, but you can't really make out who it is. And you can kind of imagine that if you're simplifying like this and you're trying to linearize these relationships and you're trying maybe to use less equations, it's almost like using less pixels in an image. And so eventually there's going to be like this kind of simplification means there's just straight up just less models. There's less kinds of models. So we know that many of the things that we observed have this really weird nonlinear behavior. If you're looking at all your other subjects, you see these crazy empirical correlations, and they're like the Prundle to the 2.3 power times, the Reynolds squared divided by, and it's like, and then you look at like what are the definitions of those things, and they're like complicated as well. So you get complicated relationships with complicated numbers, and what we're saying is, okay, so within the area that we're working with, like U is about 50. So that's a big simplification, right? That goes from a lot of equations down to few equations. Now, at some point, a realistic kind of temptation arises to completely skip this first part, which is like, well, we know now how first order systems behave, right? And we know that, and I've asked you to do this in tests. I've said something like, or I've at least asked you to do this in prep for tests, I've said, look, I'm going to draw you a curve like this. And I expect you to say, you know what, that looks, it's not a first order response, but it looks like a second order response maybe. You know, it's got maybe a time constant around there because I know kind of what the time constant behavior looks like. It looks like it has a gain that you can kind of read off over there. So that resembles a second order system. And now notice in that process, I have not spent any time thinking about any of the stuff from theme 1. Right? I haven't done geometry, I haven't thought about heat transfer, I haven't thought about the governing equations of momentum or any of that. I've just said, well, I know what these responses look like. That looks like a second order response. I can see it's kind of overdamped. So I know kind of what that's going to look like. And I can guess, I think most of the people sitting here would kind of guess, okay, zeta maybe like 1.5, tau, whatever that intercept is there. Gain, whatever, you know, so you can kind of work that way. And that's kind of what we're doing in study theme 6 at the beginning. So when you look at the methods from the beginning of study theme 6, you'll see these response curve methods that I've asked you to do intuitively. You're going to do that much more systematically. So there are people who have written down rules. And the rules look something like, you know, if you have a first order plus dead time system, you know, you can kind of say that you can read the dead time off over here. Let's just zoom into that. You can read the dead time off over there. Everybody should be familiar with the first order box, right? So you can kind of say, I can either do a tangential, I can kind of construct a tangent line on that initial value over there, or I can just straight up read off when we get to 63% of the final response, if it's a step response, and so that'll give me tau. And then the gain of the transfer function, remember, so if we're going, let me just maybe make that a tau. If we're going for the gain of the system, remember, we think about the gain as being this delta y divided by whatever the size of the input was that we had to do to make that step. And we've spent a lot of time thinking about unit step responses. So it's important to understand that in real engineering units, it's very unlikely that you'll be doing a unit step. Right? Like if you're moving a valve which goes from 0% open to 100% open, it's unlikely that you'll change the valve position from 0 to 1. You'll probably change it from 50% to 60% so that the people on site don't kill you because like you're completely messing up the whole system. So you're making these changes that are small enough that you don't mess up too much, but that are big enough so that you rise above what is called the noise floor for that system, because in reality, all of these things are slightly complicated by the fact that when we make real measurements, they never look the way the textbook measurements look. Right? They never look like these perfectly smooth lines. They always look like these fuzzy, hairy lines. And that makes some of these techniques a little bit more difficult. So the complication of identification is that if it were this perfect world, if we just exactly got those responses, we could use those methods and we would get 100% correct result. So if you just take a first order plus dead time system, you simulate the first order plus dead time system, you can recover exactly those parameters by just choosing, and so by just either drawing this like this, or you could just write down the actual function. So you can write down that function, you can write it down 2 times, if you just want to find the gain and the time constant. And you just choose any arbitrary 2 points. So I can say at this point, I choose those values, and I can just solve for the 2 unknowns. If I had that crisp line, that's all I would need. But the problem is with these hairy bits, maybe like something goes wrong and I actually get a measurement that's there. right? Which means that when I go and I solve those parameters, I actually get a curve that now perfectly goes through these two measured points, but doesn't actually go that well through the totality of the curve that I'm looking at. And that kind of motivates this idea that maybe it's better to use all of the data that I have, rather than just using 1 or 2 points. And last week, or very many weeks ago when we spoke last during this lecture, this was the take home that I wanted you to take home, which is that these old methods that are based on small numbers of measurements, or kind of these procedures that are based on a very pure step response, in my personal opinion, are not very well suited to the realities of modern industrial data. You'll remember that we spoke about like having machines that actually drew these kinds of graphs. In many cases, those machines were designed in such a way so that they minimized this hairy noise effect, but also they were working through computational challenges, which are that they didn't have computers to do their computations with. And so they and you'll see this legacy, you will have encountered this legacy in many of your textbooks, in Perry, in many of the books that have correlations. There are tables and figures that allow you to calculate things that you could really just calculate on a calculator. What's important to me is the intuitive understanding, right? So I do kind of expect you to be able to at least construct that box and work backwards from a step response to kind of understanding what roughly the parameters are. But if you're doing this in anger, if you're really wanting the actual parameters, there's a much better way, and I'm going to show it to you now. Okay, so just understand where all of this is coming from. So I'm not going to go into the second order fitting models. I'm not going to go into the deep methods. In my personal opinion, the codified versions of those, the non-intuitive versions of those, are effectively useless. They fulfill a purpose that is no longer necessary. So this is why I keep hammering on the intuitive part, because I think there's huge value in being able to do this with your brain. Look at it and say, that looks like a time constant of about 20. That's huge. Being able to like look at it, estimate a value like that, right? But having memorized it and being able to perform the procedure, if you're going to use a computer, you might as well just use the proper methods that I'm going to show you now. The basics of linear regression. And as I said, I'm going to show you these. I'm going to gloss over the details because honestly, I don't expect you to derive these values. The thing that I want you to understand about linear regression specifically is that it involves linear algebra and it has a closed form solution. Now those two facts tell you that it is fast, and the fact that it is a closed form solution tells you that it is this thing that I'm talking about where you don't need any guessing. Okay? So, okay, let me just fast forward to the actual example. So this is the data from example 6.1 in Seaborg. It's the same data I've just entered into this Excel file. And I think most of you are very comfortable with, if you were to open this in Excel, like to fit a line to that, you right click, you say add trend line. Okay, and so we've got this thing, we've got the linear regression already put in there. And the thing that I want you to kind of just ponder for 2 seconds, now weirdly you should have actually done this in stats, but my experience is that they don't really go over this very well in stats. But I have an interesting question for you to ponder while I'm going through the spiel. Why is it that Excel doesn't have a little entry box here that just allows you to put the formula that you want to fit right there? Like, why only these? What's special about these things that are in these radio boxes? So I'll tell you why, in the form of the solution that I'm going to present in the notebooks. It's called least squares regression. And so we can see that that's a straight line, and we can fit that straight line in Excel. If we were doing this from first principles, this is what that would look like. Okay? So I've got these points, and you can see I've got 1, 2, 3, and so on. That's the first point, that's the second point, that's the third point. And I can write down, and I'm starting with index 0 just because Python likes index 0. In the same way, and remember when I said we could sample points on this curve, right? And I could write down the equation that describes the response. I could write down this equation twice. and then I could just solve for the two unknowns. Okay? I could follow exactly that same approach if I write down that linear line, or that linear expression there. I can write that down, and I can write it down once for every known data point. But I want you to understand something very, very important. Even though I'm using symbols for y0 and x0, by the time I write it down, it's going to be a value, right? So y0 is going to be exactly the value 2. And x0 is going to be exactly the value 1. That is at 1, 2, right? And so that's going to be 2 is equal to, that's going to be like y0 is equal to x0 times m plus c, m times 1 plus c. And then the next one is going to be like the next value, and the next one, and I could fit the line by just using 2 points. Absolutely doable, right? So like if I do it using 2 points, that's easy. It's like solve this equation simultaneously, no problem. What if I have all these many points? Well, then I won't necessarily get a point that goes through all the lines. So I need to define some criteria to figure out the line that I actually take through these points. And what we're going to be doing, and I'm slipping in a little bit of matrix notation here because that's kind of fundamentally how these things actually get built. So just take a little bit of time to understand this equation that's on the screen right now. You can understand that like when I write down all of those equations, they form a system of linear equations. And notice that the matrices y and x contain all known coefficients. Also, be very careful that you understand that this column of 1s corresponds to this b constant over there. Right? So everything always has a 1 coefficient. Like if it's invisible, it's a 1 if you multiply, right? And these things are actually the things that we're solving for. Okay? And by now it should be kind of familiar to you, this idea that when we solve equations, you should feel this kind of urge by now using computers and so on to like write them in the residual form, right? You're like, oh, okay, cool. I know that usually when we're solving equations using a computer, we're trying to set the residuals equal to 0. Root finding almost always works this way. So like that urge is a good urge because this is exactly what happens. We have this kind of residual term, which is the difference between the left-hand side and the right-hand side of that equation. And my best intuition for why we're doing least squares minimization is this idea that this thing is a vector, epsilon is a vector. And one way of thinking about what we're trying to do is maybe we want to make epsilon small. But what does that mean when I have a vector epsilon? One way of thinking about the size of a vector is to calculate its norm, right? So you've done this many times before. So remember, if I have a line or a vector like this, the magnitude of the vector, right, is the norm of the vector. And if it's 2-dimensional, it's like Pythagoras. But if it's n-dimensional, we can generalize that general formula and just say, well, we're adding lots of squares together and then taking the square root, which is exactly the kind of formula that we have here, right? So that's the formula for what is known as the Euclidean norm, which is effectively just like the n-dimensional generalization of Pythagoras. So if you know Pythagoras, you already know this, but like in general form. So for a 2 vector, that is just Pythagoras. Okay. One important thing to notice about this, and if you know nothing about math, other than, or if I just gave you this in your second year and said, like, I wrote out all these formulas and I told you, like, find the minimum of this with respect to A, what would you do? You would take the derivative with respect to each of the variables, and you would set that derivative equal to 0. Am I right? The derivative of this thing, which is let's say the derivative of this thing, is a linear equation, or a set of linear equations. Does that make sense? I start with the quadratic, I take the derivative, I end up with a linear system. Right? That's the only intuition I really want to get. I mean, you can go through the proof. There's tons of proofs of this. As long as I have you there, that you understand, okay, I started with this quadratic, and why am I saying I'm starting with the quadratic when I have this nasty square root here? The square root has this nice thing that the square root function is what is called a monotonic function. In other words, it only ever goes up. And so if I find the minimum of something, I have also found the minimum of its square root. Right? Because it's one-to-one. There's no way to find, there's no weird stuff that'll happen if I just square the error. I'll get the same result because the square root is monotonic. And actually, I'm squaring it because having that quadratic term there is hugely valuable. Because if I take the derivative of a quadratic, I end up with a linear system. And by now, you should have heard me say this many times, we love linear systems. Linear systems are awesome because they have beautiful, defined solutions. Yes?
What about the negatives in the residual when you do the differential?
No, there are no negatives in the differential. So remember, even if I take the square root, so look at that, right? If I have this thing for the
you say that you often relegate. It says you often drop the square root to make calculations easier.
Correct. And so understand that by the time I square that residual, it's already positive.
Yes.
So taking the square root, I'm just taking the square root. This is an important point. The square root is neither here nor there because of this fact that it is monotonic. Minimizing that expression is the same as minimizing the expression of that thing squared. Like it's the same number because it's one-to-one. There's a one-to-one correspondence. So I don't lose anything by dropping the square root, right? Does that make sense? So because I'm never taking this is never imaginary. It's always just real stuff. There's no weird stuff there. So I can square it and I lose nothing, but I gain a lot. I gain the ability to take the derivative and then set that derivative equal to 0 and actually solve that equation analytically because I have a linear system. Now, I don't expect you to do that. I just expect you to understand that this solution exists, right? And that's what it looks like. Now, I don't even expect you to memorize this because I expect you never to use this formula ever in your life. Okay? So this is why I'm saying, this is you can actually get there, but this is more like a fun thing that says, oh, look, if we do the math, this is very much it does actually work. Just don't do it. Which is why I think I should actually have this right at the end. There's a little bit of construction of these functions in your own time. Use the question mark, figure out what's happening. So I'm building y and x, which are these matrices over here, by basically taking that y vector and making it two-dimensional and making it a column vector, and then taking these things and kind of stacking the x and the ones next to one another. So I'm taking the x and the ones, I'm stacking them next together. This BMAT stands for block matrix, so it's you pass it blocks of other matrices and it stacks it into a box. And behold, if I evaluate the formula, I get the correct answer. Please note, you should never do this. Okay, I've tried being very clear. I'm going to leave that on the screen for a minute. Absolutely never do this. Okay, never use this formula really for production because it is numerically badly behaved. In some cases, you may be forced to do this, and I've added in this Excel expression. You can actually do this in Excel. The reason why I say you should never do this in production in Python is because there are library functions that do this much better and much more reliably, and in fact much easier than constructing these matrices. So why is it useful to know this? It's useful firstly to understand kind of what's happening. So it's not doing any iterative solving, it's not doing numeric methods or anything like that. It's plugging stuff. It's solving a system of linear equations, but it's doing it nicely. Also, it's useful when you have a form that is not well handled by the built-in functions. One specific edge case, which is not well handled by the built-in functions in NumPy, for instance, is fitting a linear function without without the intercept. In other words, without having a b. So the tool that I recommend that you use if you're just fitting general polynomials like this is called polyfit. And you'll see that there's a ton of different numpy.poly functions. They all start with poly. And so you can add polynomials together, you can multiply them, you can divide them, you can get the derivatives and integrals of polynomials. Because that's a really straightforward operation, this is very well automated in NumPy. And so if you're just trying to fit a first order polynomial to this data, please just use polyfit. Key problem, right, is that in Excel, when we look at the regression options, there's a really nice option here that allows you to set the intercept. So in Excel, that's like a little checkbox, and you set the intercept and you type 0. And unfortunately, there is no equivalent option to polyfit. So there's no easy way to tell polyfit, don't fit the C term. And when you're thinking like, why is there not that option? Well, there isn't that option. It's just how it is. There is no option like that. Now, so how do I do that? You basically do this method, but you use definitely linear least squares to do the solving. So this function, numpy.linear.least squares, effectively solves this problem, but from the original form. In other words, it basically says, I have something like this. I know that there's this analytic solution, but I'm going to solve that problem without doing that inverse, which is what makes the system numerically badly behaved. And so if you want to fit this system without the intercept, you simply construct the y and the x, but you leave out this constant column, which then constructs the problem with an intercept of 0. Right? If you want to solve it with an intercept that is not 0, you then have to subtract that intercept from the y data, because there's no easy way to just handle that in the problem formulation. I'm sorry to say that, but that's just the way that it is. Polyfit also allows you to fit higher order polynomials. And one thing that I really advise you to do, when you're doing polyfit, I really hate the way that Excel handles higher order fits, because if I take a polynomial and I fit like an 8th order polynomial or like a 6th order polynomial, it looks artificially amazing on the plot because Excel only evaluates the polynomial at the function values. And then it uses this kind of smoothing function that smooths between the points. So it's not actually, that dotted line is not actually giving you the value of the polynomial that you fit in the intermediate points. I hope everybody is clear on that. Which is why I very much prefer to evaluate that. I would like to do that myself and evaluate on a finer mesh. So if you're just using the normal options on plotting, a lot of times what you're going to do is you're just going to connect those values with straight lines. And I've illustrated this effect over here, right? So I've done a large number of points. I've done an 8th order fit, right? And you can see that 8th order fit has this very undesirable little bounce between data points 1 and 2. This would be invisible in Excel. Right? So I would get a value, I would get a polynomial. The polynomial would go through the points really well, but it would have this really bad behavior in between points, and I wouldn't even know about it because Excel isn't actually plotting the polynomial, it's plotting some smooth spline between the points. So you have to be aware of this because it's a very big danger, especially when you're starting to fit relatively high order polynomials. Okay, so when you're doing normal linear regression, my tool that I recommend is polyfit. So, what do all of these functions have in common? All of these fitting functions that Excel has, what do they have in common? They all have forms that are either directly writable in that matrix form or writable in that form with minor modifications. So when I say minor modifications, if I have something like y is equal to b log x, right? That by itself is already linear in the coefficients, right? Because remember, this whole thing is known at the point of evaluation. So I can do that with linear fitting, no problem, okay? What if I have something like y is equal to a times x to the b, which is like the exponential model that they have? Well, I can take logs. Right? And now again, I have a system where the coefficients are where the known bits or the coefficients are linear in the equations. Now notice here, I'm going to have to do a little bit of extra work because the polyfit solution will give me log a. And then I've got to remember that I had log a, and then I have to take the exponential to get back. But this in total completely explains the list. Every single one of these functions is either already, for the polynomials, or can be manipulated into a form where the coefficients appear linearly in the equations. Now that's why that list exists, because those are the things that Excel can guarantee a good value for. I'm going to run long, it's okay. Okay, so is everybody with me on linear regression? So when you see linear regression, you should favor linear regression above every other form of curve fitting. And I'm going to explain to you why. And I want you to kind of now, if you like writing notes in your book, right, make like the biggest, most scary warning sign that you can make for yourself, because this is almost like, I'm going to like give you like just a little sniff of cocaine, right? It's going to feel amazing. And then I'm going to tell you, listen, really, you shouldn't be doing this a lot, right? It's bad for you, okay? Let me explain. When you do nonlinear regression, and I'm trying to rather use the word fitting to kind of distinguish here. Almost everybody that I've spoken to about this prefers this maybe 100 times above the previous version of the solution. Okay? This is going to feel amazing because it is obvious how to use it. Right? Plus, it has this wonderful thing that everybody's looking for. This is the one tool. This is like the multi-purpose tool. Okay? It works for linear, it slices, it dices, linear, non-linear. Like you just put your formula in there. Right? Copy this notebook, delete all the other stuff, put the formula that you're looking for in there, run it, and you're done. Okay, that's the idea. That's what it looks like. So this is possible. In other words, there is this thing called curve fit, and I want you to understand what is happening behind the scenes. In the previous, when we're doing polyfit, okay, remember, a key thing that we did not have to do in polyfit that we're doing here, if you look at the function signature of curve fit, and I mean, you can read faster than I can talk, and it's really boring for me to read code. But basically, you define a function that is the function you're trying to fit, and then you call curve fit, and you call it with f, and you call it with x and y, which are the data that you're trying to fit, and then this list over here are your guess for kind of what the parameters are. And that's like already a clue that maybe this is not as awesome as it seemed at first, right? Because this is like this weird, like, circular argument. It's like, to use curve fit properly, you actually already need to know what the parameters are before you can use it. This was not true for linear regression. For linear regression, you just needed the data, you did the thing, you got the answer, no guessing required. Now we need guessing. And a lot of you are thinking, but wait a minute, Carl, just look how amazing it works. It works amazing. I put the stuff in there, I get exactly the same answer. It's a lot easier to understand. Like, I define the function, it's generalizable in the copy and paste sense, in the sense that if I copy and paste this, I will understand what to change in order to solve my new problem. I just write the code in there, change the parameters over there, and I make a new guess. This is why I built this new function, because I saw far too many people taking out of this lecture only this result, which is like blah, 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 curve fit. Okay, that sticks in people's minds. It's like, oh yes, there was all this other stuff which was impossible to understand. And then there was this thing which was called curve fit, which is this thing that I want to do when I do curve fitting. And it was like easy to use, but I want to show you that it breaks. Okay, so here's a problem that I'm going to build some data points using a formula that we can all see on the screen. Okay, it's 2 times sine of 3 times x plus 1. So I'm choosing a couple of x points, I'm evaluating that exact function, right? And I'm using again my wonderful optimized curve fit, and this is not exactly what I expected. The correct answer is 2, 3, 1 for the coefficients, right? Like that's the right answer because that's the values that I put in the formula to start the point off with. Why doesn't it work? Well, because I didn't guess right. So now I'm not getting good values because I didn't guess well, right? So those initial guess values don't get me to the right point, okay? It gets even worse because a lot of you are saying, dude, that's not a problem. That's not a problem. I just guess again, right? Like if I guess another value, like that's obviously wrong because it's like super far away from the points. I'll just guess another point and get one that goes through the points and that'll give me the right answer, right? So like this, right? Like that. That is now exactly correct. Does everybody agree that is right? So that's what I expected in the initial version, right? Like, so I've guessed some new points now, and now I'm getting some good points. Okay, cool. But let me show you something. Okay, that's the error of the fit. That's like the sum of the squares. Check this out. Would you know, if you saw that result, that you hadn't got the right values? But they're the wrong values. Provably they're the wrong values. We know the correct answer is 2311. This is 2911. It's not right. Okay? This is the bad. This is the downside on two sides, right? This is the downside of using nonlinear model shapes, right? Because they have this problem that, like, if we're not in a linear mode, we can't guarantee uniqueness of the solution. Those two fits are the same in terms of quality of fit. They both go through all the points exactly. But the one is right and the other one is wrong, right? And so I want you to remember this, and I want you to do just one thing, which is try to start with linear fits first. And try to choose model shapes that don't have this problem of multiplicity.